This lesson goes through some algebraic properties of limits, which will help you to calculate limits when you're given the equation of a function. So, properties of limits. Property number 1. The limit as x approaches c of x equals c. What does that mean? Let's look at an example. So what we'll do is for each property of limits, we'll look at an example and how that helps you calculate the limit. So let's say we want to try to find the limit of x as x approaches 2. That says, our property says that is equal to the number we're approaching, so that is just equal to 2. You can think of it as where the line y equals x is going towards if you want to think of it graphically. Okay. So if we have a constant function, let's say the limit of a as x approaches c, where a is some constant, that is going to be equal to a. You can think of that as like a horizontal line. So an example here would be, let's say the limit of 5 as x approaches 2. Well, if our function is always 5, we don't really care what x is doing. So that is still going to be equal to 5. Okay. So what happens if we have a constant multiplying our function? So if we have the limit of alpha times f of x, where alpha is some constant, as x approaches c, that is equal to alpha times the limit of f of x as x approaches c. So we can take the limit first, and we can take the limit of that function. That is the same as just the number times the limit of the function. So our example here, let's say we have the limit of 5x as x approaches minus 2. That is going to be 5 times the limit of x as x approaches minus 2. The limit of x as x approaches to minus 2 is just minus 2. So this is 5 times minus 2, or minus 10. Let's shrink that so you can see that the whole way through. All right, so that's with a constant multiplier. What if we multiply two functions? Well, the limit as x approaches c of f of x times g of x, the product of two functions, is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. So limits multiply. If we're multiplying two functions, that's the product of the limit of a product is the same as the product of the limits. So for example, if we have the limit as x approaches minus 2 of x squared, this is equal to the limit as x approaches minus 2 of x times x, which is equal to the limit of x as x approaches minus 2 times the limit of x as x approaches minus 2, which is equal to minus 2 times minus 2, which equals positive 4. And so as you can see, this rule actually allows us to generalize limits to powers. So we can plug in a variable. This is what this is essentially saying, is as long as we're just multiplying two functions, and we're going to see it's true for adding and subtracting as well, we can just add or subtract the limits of each x that's involved in the functions and do those same operations to the x. So what that means is essentially to find the limit, we are kind of just plugging in the number in this case. So next, what if we are adding or subtracting? So the limit as x approaches c of f of x plus or minus g of x is the same as the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. Okay, and we don't technically need the minus because we can use our constant multiplier, so it could be a negative, and we can use -1 for that. But this works pretty well. And so what that means is that if we're adding any two functions, that can work. So let's take our previous result. So that gives us the limit as x approaches -2 of x plus x squared. So we saw with the last one that for x squared, we can just square the x and see what that comes out to be. So this is the limit as x approaches -2 of x plus the limit as x approaches -2 of x squared, which is -2 plus 4, which is +2. Okay. So number 6 property. This basically now with the previous 3 properties, we can extend this idea to all of polynomials. Okay, so if p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus a1 x plus a naught, then the limit as x approaches c of p of x is equal to p of c. And this is not just true for polynomials, but this is going to end up being true for any function that is continuous everywhere. And so for any polynomial, all polynomials are continuous everywhere. There's no kind of holes in the domain or places where the function doesn't connect. It's always a straight, a curved, smooth, continuous function for a polynomial. So, for example, here, if we have the limit as x approaches -2 of f of x cubed plus 3x minus 4. So if you have more than one term and you're trying to take the limit, please do make sure you put brackets around it because you are taking the limit of multiple things added, and it would read the limit of just the first bit plus the other stuff if you don't put brackets around it. So this will be 5 to the -2, 5 times -2 cubed plus 3 times -2 minus 4, which gives us, works out to be -8, -40, minus 6 minus 4, which is -50. Okay. Number 7, 8, and 9 have to do with what happens when we divide functions. And this is where things start to get interesting. Because when we have functions that are being divided, we do open up the possibility for there to be some holes in the domain, and there are going to be discontinuities in these functions. So part of what happens with limits here depends on whether we're going to run into a discontinuity at the point we're trying to take the limit of. So our first situation, we have the limit as x approaches c of f of x over g of x, and we're going to set the little caveat, okay, where the limit as x approaches c of g of x is not equal to 0. So we have some function and we know that the limit as x approaches c is not 0 for the function in the denominator. Then this is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. So the rule for the division is fine as long as for the point c, the g of x is not approaching 0, as long as we pick a nice point, which is the vast majority of all points for these functions where you are dividing. So, for example, what would that look like? So let's say we have the limit as x approaches minus 1 of 3x plus 1 over 2x squared minus 5x minus 3. Okay, so I plug in minus 1 just to see what's happening in the denominator. We get 2 plus 5 minus 3, which is 7 minus 3, which is 4. 4 is perfectly fine to have in the denominator. So we're not approaching 0 as x in the denominator as x approaches minus 1. So I can just go ahead and say, well, this is equal to the limit as x approaches minus 1 of 3x plus 1 over the limit as x approaches minus 1 of 2x squared minus 5x minus 3. And then I can just go ahead and plug in my points. So this is equal to 3 times minus 1 plus 1 over 2 times minus 1 squared minus 5 times minus 1 minus 3. The numerator is going to give me, at the top will give me minus 3 plus 1 is minus 2, and the denominator gives me positive 2 plus 5 is 7, minus 3 is 4, so negative 2 over 4, which is negative 1/2, and that will be the y value that we're approaching. And if we were to look at the graph of this function, this whole rational function that we have, that would be the x at x equals negative 1, our y would be negative 1/2, and there wouldn't be an asymptote there, and there wouldn't be a hole there. So that's our happy situation when we have division. Okay, so the second situation we might run into is where we have the limit as x approaches c of f of x over g of x, and we have a denominator where g of x, the limit, sorry, not g of x, where the limit as x approaches c of g of x equals 0, and the limit as x approaches c of f of x is not equal to 0. So we have a 0 in the, when we plug in, the limit of the bottom function is going to 0, and the limit of the top function is not going to 0. So it's going to some other number. Okay, then we get this limit does not exist. Okay, the limit does not exist if we have a 0 in the if we're going to a 0 in the denominator and we're going to some non-zero number in the numerator. So what would that look like? So we have, let's say we have the limit as x approaches 2, not 0, sorry, 2, of 3x minus 7 over x squared minus 4. Okay, so as we take the limit, we're going to try just plugging in our numbers. This gives us, so we have, we're not quite sure. We're going to take a look. So the limit as x approaches 2 of 3x minus 7 equals 6 minus 7, which is negative 1. And the limit as x approaches 2 of x squared minus 4 equals 0. Okay, notice I'm not putting these in a fraction, and the reason is because this is not equal to this. We can't say that something that does not exist is equal to something else that does not exist. So this is going to be undefined because we would end up with a negative 1 over 0. So we say that because we have a 0 in the denominator and not in the numerator, because negative 1 over 0 is undefined, the limit does not exist. Okay, so that limit does not exist. I'm happy if you want to abbreviate does not exist as DNE. Okay, last one. So the last situation we might run into with dividing fractions is, okay, where we have the limit as x approaches c of f of x over g of x, and where the limit as x approaches c of f of x equals 0, and the limit as x approaches c of g of x also equals 0. So this is where we get 0 over 0. So we call this indeterminate. So this one, the limit may exist, and this is indeterminate. Okay? So what we want to do is we want to try to take this limit that's not going to exist. So we have some techniques that can try to make this limit exist. We want to rearrange this as much as we can. So let's take a look where this is going to happen, an example where this might happen. So if we have the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay. What we're going to try to do is we're going to try to rearrange this in a way where we get an equivalent limit. We don't really care about taking out things like removable discontinuities because we're not looking at the answer, we're looking at the limit. So we are allowed to simplify and factor things out and cancel. Okay, because we're not talking about when x is equal to 2, we're talking about what happens when x approaches 2. So this is equal to the limit as x approaches 2 of x plus 2 over x minus 2 divided by x minus 2. And we can cancel this right here. So this is equal to the limit as x approaches 2 of x plus 2, which equals 4. Okay? And if we were to look at the graph of this function, we would have a hole at the point 2, 4. It would look like a straight line, y equals x plus 2, with a hole at 2, 4. And so what happens is, okay, so the real place where most of the time, the vast majority of the time, when we're looking for the limit of f of x, we just substitute the number in that we're looking for the limit at. Because if we have a continuous function, then the limit is going to be the same as the value of the function at the number. It's where it gets discontinuous that we need to get experimental. And a lot of this unit is going to focus on some computational techniques for those points at which it's not continuous and there's a problem. So here are a few little notes on how to deal with these problems. And the next lesson will be a whole bunch of different examples of how we can work with finding limits computationally in a bunch of different situations. Okay, so when you are looking for the limit as x approaches c of f of x over g of x. And these are going to be a lot of the functions we look at is where we have some kind of fraction going on, because those are functions that will often have discontinuities. So first, try substituting x equals c into f of x over g of x. Okay, that's your first step, is actually just try substituting in. Okay, if you get a number and g of c is not equal to 0, then that is your limit. So if you sub it in and you get something, there's no zeros in the denominators, you're cool. Okay, that number is your answer. Okay, if you get f of c over 0, the limit does not exist. So you get some number over 0, the limit doesn't exist. Okay, if you get 0.
Good afternoon, staff. Sorry for the interruption. We actually have a cleaning crew that's here this evening to do a full clean of the building. So that's in preparation for Monday. So staff, unfortunately, if you are still in the building, we are going to need you to head home for the weekend so that we can have the staff come through and do a full clean, okay? Thanks very much.
Okay, sorry for that late interruption. If you get 0 over g of c, okay, then your limit is going to equal 0. Okay, so 0 in the numerator is fine. It just means that you have 0 over a number is just 0. Okay, it does actually exist in this case. And finally, if you get 0 over 0, you may get a limit if you simplify by factoring or using another technique. All right, thanks. Hope that that helps. And the next lesson will have a bunch more different examples of how to find limits in some more sticky kinds of situations.